All right, good morning, good afternoon, everyone. Thank you for joining this first presentation of the webinar series offered by HESI's Environmental Epidemiology Committee to illustrate the critical role of epidemiology in the field of quantitative risk assessment and decision-making. My name is Sandrine Deglin, and I'm the scientific program manager with HESI, and I co-manage the Environmental Epidemiology Committee with my colleague, Connie Chen. So this committee was launched about 2 years ago with the mission to foster the better integration of epidemiological data into human health risk assessment. And so if you are curious about the work that we've been doing over these past 2 years, you could join our webinar next month. The date is April 27th, and we will be presenting the work that we've done over the past 2 years, along with the work that has been done in this same space by 2 other organizations, CropLife International and the American Petroleum Institute. So just a few logistical remarks for today. This webinar is being recorded, and you will be able to view it in a few days on the Environmental Epidemiology Committee website, which is on the HESI website at hesiglobal.org. You will be able to ask your question by typing them in the question box of the webinar panel, here circled in red on the right. And your questions will be read at the end of this webinar once our speaker is finished speaking. Now, if you have any questions about this project or about HESI, feel free to contact me. Here you have my email address. My email address was also in the invite that you received for this webinar, I believe, and you can also find it on the HESI website. So now I'm going to give the floor to Dr. Igor Burstin, who is one of our committee co-chairs, who is going to introduce our speaker.
Greetings to everybody. I don't know where time zones everybody is, but hopefully you're enjoying somewhat nice weather. It is my distinct pleasure to introduce Dr. Chakaway as our first speaker of the series. He's currently a professor at University of California in San Diego in the Department of Family Medicine and Public Health. He's built a distinguished career in the field of environmental and occupational epidemiology and made significant contribution to our understanding of various occupational and environmental hazards, with particular contributions in recent years to neurological conditions, as well as very broad impact and work on occupational carcinogens that most of us will recognize today. There's hardly an area in classical occupational epi that Harvey hasn't contributed to. It is wonderful to have him today. Is perfect speaker to open the series because he does not shy away from difficult questions and aggressive questioners. As I learned when I had a pleasure to critique one of his papers in a public forum, I was utterly terrified, and he was extremely graceful and kind to young buck trying to say something clever about his research. So without any further yammering from me, I'll give you Harvey Chakaway.
Okay, thank you, Igor and Sandrine. Thank you all for joining this webinar, and I hope you find it very useful. And I'll confess my computer skills are rather deficient, so if you have some questions, I think you can type them in the chat box, and we'll leave enough time to discuss those questions. And I just want to say that I'll be talking about causal attribution and risk assessment, predominantly with examples from the cancer research, environmental cancer research, and I'll close with an example of neurologic disorders, Parkinsonism, among professional welders. And okay, we can get started. And just a couple of general points about studying environmental cancers, and these are, I think there's a rather, those of you who are experienced in epidemiology will recognize this, but cancers that are caused by environmental exposures clinically and pathologically appear essentially the same as cancers due to other causes. For instance, a lung cancer that's caused by diesel exhaust, for example, is clinically the same as a lung cancer caused by cigarette smoking, for the most part. One important point that I hope I can convey in this talk is that the workplace is considered the so-called high-dose situation. And what that means is that exposures typically in work settings are much higher than in the general environment. That's not always the case, but for the most part, we think of the high-dose situation. And we'll see some examples of both epidemiologic research in workplaces and in the general community. And it has been estimated that occupational exposures cause approximately 5% of all cancers worldwide. That sounds like a small fraction if you compare it to, say, diet, smoking, and other, air pollution, but that ignores interactions with other causes. So, like I said, a worker who is exposed to diesel exhaust and is a cigarette smoker is going to have a very, very high risk of cancer. And we'll see some examples to cover this. And I just want to make one general point, is that the examples I'm going to show you are not the most recent research findings. So there are a couple that are relatively recent, but I want to give you a perspective that goes back over the past, 20 to 30 years of, I think, very informative examples. Also, and I should have made this point at the outset, if you have any questions and you'd like to contact me, please feel free to send me an email, and I'll be happy to, we're all sort of overloaded with emails, but I'm happy to get good questions, and, I hope you find it useful. Now, there are some associations that are very well established, and between environmental factors and cancer risks. For instance, long-term overexposure to sunlight causes skin cancers, melanomas. That's been known for a long time. High-dose gamma radiation exposure has been linked with leukemias, breast cancer, lung cancers, and other cancer sites. The classic example is the Hiroshima and Nagasaki atomic bombings in World War II. Indoor radon exposure from radium concentrations in the soil. If they get into homes or workplaces, they can cause lung cancer. And drinking water that's contaminated with arsenic can lead to cancer risks of various sites: skin, lung, bladder, and liver, and perhaps even some others. These are well established. I don't think, and it does require that you have to have a substantial exposure. Not a tiny little drop of sunlight is going to cause skin cancer, but overexposure will. On the other hand, there are some situations that are considered controversial. These are listed, a few of these. One, and we'll see examples of this with dioxin. And I think you've probably heard about dioxin. If you think about Agent Orange, dioxin is the active component in Agent Orange. It's been linked with soft tissue sarcoma. It's a very rare type of cancer. Residential electromagnetic fields have been associated with various cancers. There were concerns about breast cancer, central nervous system cancers, and now the main consideration is childhood leukemia. And there's a big concern, putting electrical devices next to the kids' bodies is not the best thing to do. But it's not an established. There is some plus and minus evidence for this. Chlorinated organic compounds such as polychlorinated biphenyls, which are in electrical capacitors, have been related to various cancers: breast cancer, non-Hodgkin lymphoma, and others. Formaldehyde exposure has been linked with the leukemias and lymphomas, the so-called blood cancers. And if you think about formaldehyde in the environment, just think about the lab courses that we've all taken in school, and that smell is a lot of it is formaldehyde. You go into beauty parlors, nail salons, there's a lot of formaldehyde around. And again, you need high doses before cancer risk is associated. And glyphosate, which is the active ingredient in some herbicides, the best example of that is Roundup. It's a chemical that was produced in the United States, has been associated with non-Hodgkin lymphoma, but there again, the evidence isn't crystal clear. I mean, there are some questions about that. Now, the International Agency for Research on Cancer is a branch of the World Health Organization. I'm sure most of you have heard about IARC, and I had the good fortune about 10 years ago to do a sabbatical at IARC in Lyon, France, and it's a very good learning experience. I was involved in epidemiologic research there, and I got to learn a little bit about risk assessment from the risk assessors on these committees. And I should point out that I'm not a risk assessment expert. I'm an epidemiologist, but I have a great appreciation for risk assessment. IARC has come up with a scheme. It's very well established. There's category 1, or group 1. Those are so-called confirmed carcinogens. We'll see some examples of these. Group 2 is split into 2A, probable carcinogen, and 2B, a possible carcinogen. Group 3 is not classifiable, and we'll see explanations of what these categories mean. And group 4 is a chemical or physical agent is probably not carcinogenic. And almost nothing falls into group 4 because that's essentially, so to speak, proving a negative. Here's a listing of some of the category 1s. These are established carcinogens. And I should point out that epidemiology contributes a lot to this body of evidence, but also toxicological research is very important. And with category 1, let's just look at these. These are just in alphabetical order. But arsenic is very well established. I won't go through all of these in the interest of time, but it occurs in smelters and mines, and it contaminates some drinking water sources. And the cancers that have been induced by arsenic overexposure are lung, skin, bladder, and perhaps others. Asbestos exposure is the classic environmental carcinogen. Fortunately, it's been banned for use commercially, and mining of asbestos is not allowed in most countries worldwide, but there is still a substantial amount of asbestos exposure in the environment and some of the insulation materials in homes and schools and others. Skip down a little bit. We'll talk a little bit more about dioxin. Cadmium occurs in mining. It's in electrical batteries, and it's been linked with lung cancer. Ethylene oxide, it's in medical devices. It's been associated with elevated leukemia risks. Formaldehyde, mentioned, it's in many environments, workplaces, and the general environment. And the main association that's been established is nasopharyngeal cancer. There's some question about the blood cancers, leukemias. Ionizing radiation at high doses, there's basically no question exceptionally high levels of X-rays or gamma rays have been associated with leukemia. Radon and lung cancer, again, no question. Silica, crystalline silica, occurs in mines, in pottery manufacturing and other industries associated with lung cancer, and vinyl chloride, which is involved in the production of polyvinyl chloride. It's an insulation material, has been linked with liver cancer. Now, there are a number of approaches that are used to identify occupational carcinogens. And if you go back over time, there were case series reports. You see basically a cluster of a cancer. One of the classic examples was in Germany in the late 19th century. There was a cluster of about 5 cases of bladder cancer in an aniline dye factory in Germany. And bladder cancer is not the rarest cancer, but at the time, the main cause of bladder cancer, cigarette smoking, was not very common in 19th century Germany, and it was an unusual circumstance. Other approaches, sometimes people will dismiss case series reports. It's just a random event. Some of those are. Another case series is asbestos causing mesothelioma. It's of the lining of the lungs and the peritoneum. There is no question that that is caused by asbestos. Other approaches, which are more formal epidemiologic designs, are cohort and nested studies, nested case control studies. And then the most common approach are population-based case control studies. And we'll see examples of each of these designs. Now, let's talk about dioxin. And this is the chemical structure of dioxin. It's got kind of a long name, 2,3,7,8 tetrachlorodibenzoyl-dioxin. Basically, there are multiple different dioxins, and it depends on how many chlorine attachments there are to the main structure here. But dioxin has been associated with carcinogens, and in the Vietnam War, that was used basically to kill vegetation. The American military sprayed Agent Orange, which was contaminated with dioxin, and it did kill the plants, but perhaps it caused some cancers in the population. Now this is a listing of the known and suspected health effects of dioxin. And I should point out there are multiple different dioxins. We'll just call it dioxin. 2,3,7,8 is the main congener of dioxins. It causes a condition called chloracne. It's basically like regular acne, except it's more, your skin turns more like sandpaper. It can cause elevated liver enzymes, lipid disturbances, LDL cholesterol levels will increase. Whether it's transient or long-term has never really been established. There are questions about diabetes. Animal studies have shown adverse reproductive outcomes. And in terms of the cancers, soft tissue sarcoma, that's the so-called signature cancer linked with dioxin, non-Hodgkin lymphoma, and perhaps lung cancer. And as we'll see, there's evidence that dioxin may be a cancer promoter. It increases the carcinogenic potential of other exposures, and perhaps maybe by itself doesn't necessarily induce cancer. Now, one of the classic examples in environmental epidemiology was the Seveso, Italy study, and I'll just run through some of the episode events. In July 1976, there was a big explosion of a trichlorophenol manufacturing plant in Seveso, and the plant literally blew up. And within hours or days, vegetation died. The domestic animals and other animals, the cattle and the sheep, died within days or weeks. And the Italian government, to their credit, undertook an exposure modeling approach, did soil sampling studies. There was a survey done of chloracne and blood dioxin levels. And we'll see some of the findings from this work. And there was a follow-up study of approximately 250,000 people who were living in the Seveso area. That's in northern Italy. It's near Milan. And I should point out Seveso it was at one time the furniture manufacturing capital of Italy and perhaps of Europe. And after this episode, all these terrible events that occurred, people stopped buying furniture that was manufactured in Seveso. Apologies for the rather crude looking diagram. I got this from an old archive. This shows, this is the plant, the PCP plant here, and this is Seveso, this hatched area. And this is what's known as Zone A, that had the highest exposures. The more densely hatched area, Zone B, had lesser exposures, and Zone R, which is the open areas or the reference zone, basically just background levels of dioxin. And here are the results of the soil sampling survey that was undertaken by the Italian government. And if you look in Zone A, relatively small population, but the concentrations, there's a broad range, which is quite typical of environmental exposures, much higher than Zone B. And Zone R, the reference zone, less than 5 milligrams per meter squared of soil. And this, by the way, reference area, Zone R, it gets a little confusing when you read the literature, but originally Zone R was called the reference area. That was the area surrounding outside of Seveso. And that was since called the zone of respect because the reference area was a much broader part. It was redefined as northern Italy near Milan. Well, here are the results. This shows the prevalence of chloracne, which is a biological clinical marker of dioxin exposure. And this is the prevalence, Zone A. That's the highest exposures right near the facility, 81 per thousand. Zone B, a little over 2 per thousand. Zone R, zone of respect, 2. And the reference area, just the background levels, less than 1. And you can see that this, if you take the classic clinical feature of dioxin exposure, Zone A had the much highest exposure. Of course, from an epidemiologic perspective, it's a small population. Here are the results. This is mortality and of different cancer types, Zone A, B, and Zone R. And this is the reference area. And all cancers, just to combine them, it's a rather broad classification. No association. This is comparing rates with the national rates in Italy during that time period. Lung cancer, very small excess in Zone A. Soft tissue sarcoma, which is the classic clinical feature, it's not a fatal disease for the most part. So there were not enough cases for determining relative risks. And non-Hodgkin lymphoma, which was somewhat of a surprise finding, showed a relative risk of over 3, but there again, small numbers. And keep in mind, this is mortality, and it's a relatively small population. Now, another analysis that was done by colleagues at the University of Milan, this publication by Consoni et al., shows the findings for cancer mortality, all sites combined. And if you look at time since exposure, you see a trend suggesting that greater than 20 years after the explosion, this is Zone A, all sites combined, there was an elevated relative risk, 1.7. And just back up here. By the way, IARC, when they classified dioxin as a category 1, a so-called confirmed carcinogen, this finding was, even though the numbers are relatively small, was very influential. What was more influential than the epidemiologic research was the animal studies, the toxicology studies in non-human primates that definitely showed carcinogenic potential. So when we get to the point of risk assessment, epidemiology makes a major contribution, but we can never forget the importance of toxicological research. Now, I want to move on to an epidemiologic study, a cohort study that I led some years ago when I was at faculty at the University of Washington. And this is a study of crystalline silica and lung cancer in diatomaceous earth workers in California. And in 1987, the prompt for this research was in 1987, IARC classified crystalline silica, which you find in sand and soil and in pottery manufacturing, other processes, categorized it as a probable human carcinogen, category 2A. And the diatomaceous earth industry in Lompoc, California, which is a little bit north of Los Angeles, and they had a long history of silicosis, which is scarring of the lung, and there was concern that perhaps after the industry heard that IARC had classified it as a probable human carcinogen, there was concern that people with silicosis who had relatively high exposures might have had an elevated lung cancer risk. And an industry association called the International Diatomite Industry Association sponsored an epidemiologic research study that we conducted, and we were approached by the diatomite industry and asked if we would be interested in studying possible cancer risks related to diatomaceous earth exposure, and we said yes, with the understanding that the industry would not try to influence how we did the research, but rather they would provide us with obviously the resources, the funding to do the work, and access to the workers and medical history and work histories and exposure. Just a little background on diatomaceous earth. These are diatoms. They're almost like little slugs that occur in the soil and the water. And when they die, they're during life, they concentrate, diatoms concentrate silica into their exoskeleton. And when they die, this is what, these are photomicrographs of exoskeletons of diatoms. And the process is, it's a very simple process in terms of manufacturing. Importantly, it's an open pit. I'll show you some pictures of this. It's an open pit quarry of mining, and the mines and the diatomaceous earth is mined, it's crushed, and it's put into a plant, basically into a kiln, and it's almost like a pottery factory, and it produces powders, and the diatomaceous earth is produced in that manner. And by the way, diatomaceous earth is used to kill, creatures, slugs. It's used to protect some gardens from, pests, and it has some value. It's also mostly commercially, it was used as a filtering agent for drinking water and commercially soft drinks, materials like that. So it had a lot of, industrial and commercial uses. This is a picture that the industry provided to us, and it shows the mining. This goes back to the 1930s, and notably, you see it's a rather primitive-looking operation. It's open pit, which means that there wasn't, you weren't concerned about radon exposure, such as in underground mining, but it's a rather crude-looking operation. And most of the workers, this is in Lompoc, California, were Mexican immigrants who were brought over to the US to work in the diatomaceous earth mines, and they lived in little villages that were set up by the industry. It sounds rather primitive by today's standards. You can't imagine living in an open pit quarry, but this is what people did back then. This is a more updated version. This was a picture taken in the early 1980s of diatomaceous earth mining, which is in the manufacturing and the mining was much more advanced than back in the 1930s and 40s. And this historically has an important context. This is a picture of inside one of the diatomaceous earth factories, and this is a picture from the 1950s, and it shows material has been put in kilns, it's been ground up, and it was then put into these lined paper sacks. That doesn't seem like a big technological advance, but before the 1950s, they were just put in burlap sacks, and when the sacks were stacked up, there was dust all over the place. And another important point is that the workers were provided with respiratory protection. Doesn't look very sophisticated protection, but prior to the 1950s, people worked with no respiratory protection. And what triggered this was that the workers were unionized, and the union was very concerned, appropriately, about the health of the workers who were developing silicosis, lung scarring. And this was a process. And you'll see Johns Manville, that may be a name that's familiar to a lot of you. It's a company that basically mined and sold asbestos. They were also the owners of this diatomaceous earth facility. Well, here are the findings for silicosis in the diatomaceous earth industry. And the industry provided us with their air monitoring sample in the plants, and also some of the outdoor samples. And we were able to come up with a cumulative exposure metric of milligrams per cubic meter times years. And this is for silicosis, which silica causes silicosis. And not surprisingly, you see a very strong dose-response relation, relative risk of over 40. And colleagues that I worked with at Tulane University, Hans Weil and Janet Hughes, were pulmonologists who were involved in this research. And the important feature of this, in terms of the cancer research, was that it appeared as though our exposure classification was appropriate, because we saw a very strong dose-response trend for silicosis. Here are the mortality results, and this was our first follow-up as a historical cohort. It went back to the 1940s. They were followed through 1994. And if you look at all causes, there was no excess. I mean, all causes is kind of a vague classification. We didn't see the so-called healthy worker effect, but still we didn't see any excess risk for all causes. Lung cancer, only a small excess risk, 1.3. And non-malignant respiratory disease, which is obstructive lung disease, and includes silicosis, a relative risk of 2. But the findings were not remarkable if you just look at these broad categories. However, when we did the dose response analysis for crystalline silica and lung cancer, we did see a very striking dose response trend. It's not enormous like you see for high dose radon or asbestos, but we did see a trend, and for what it's worth, it was statistically significant. And at the highest cumulative exposure level, we saw a relative risk of about 2, and this was statistically significant. Now, we did an extended follow-up, and just a little bit of background on how that happened. Our contract, I'll just back up here, our contract was to study historically from 1942 to 1992, and we were doing the study in the late 1980s and early 1990s. I'm sorry, mid 1990s, and the follow-up was funded by the industry, and we told them that our findings were, clearly indicative of a lung cancer risk, and we asked the industry if they would be willing to support an extended follow-up. And their answer was no, because IARC, part of the reason was that IARC changed the classification of crystalline silica from category 2A to category 1, confirmed human carcinogen. And we asked them, would they be willing to fund it? And they said no. It's sort of understandable. The industry got bad news, and this led to a bunch of risk assessments for, crystalline silica and lung cancer. And we were able to get funding from National Institute of Occupational Safety and Health, and did an extended follow-up through 2011. And this is the dose response trend that we saw for the extended follow-up. And basically, the relative risk trend held up, and our findings for here were not just artifacts. They did persist over a long time period. I don't have a slide to show you, but if we just look at the findings for the second follow-up, they're smaller numbers, but they also showed a dose response. Now, I want to move on to another more controversial exposure, and that's glyphosate. And as mentioned, glyphosate is used in herbicides, and it kills weeds. And it's mainly used, to kill, commercially to kill weeds. It's spread on a lot of crops, and people even use it in their home gardens. But it was found to be toxicologically damaging, and it gets into soil, into food, and it causes some non-cancer effects, dermatitis, throat and eye irritation, and mainly based on toxicological research. IARC classified glyphosate. The main product is Roundup. It was classified as a probable human carcinogen, mainly based on animal studies. And there is ongoing concern by the industry. It was manufactured by Monsanto, and now it's Bayer Chemical. That's the owners of the glyphosate process, but it's been widely banned in many instances. And to tell you the truth, it's not a good product. Glyphosate, it kills weeds, but it also kills your garden, and it can kill your pets. And there's big concern about it, but commercially it's very effective. There has not been substantial research on glyphosate, and perhaps the most convincing study, or the largest study that's been conducted so far, was a study of pesticide applicators in Iowa and North Carolina. That's a study that's funded by the National Institute of Environmental Health Sciences, and they study pesticides, other agricultural exposures in Iowa and North Carolina, and they've been doing lots of different studies of cancers, pulmonary disease, Parkinsonism, and others. And basically, the relative risk trend shows no association. And you might say, well, this is cumulative exposure. It's a very good exposure classification, but there's no excess risk trends. And you might say, well, no harm, no foul, so to speak. But really, much more research is needed to be done on glyphosate exposures. Whether occupational cohorts can be established or residential cohorts can be established remains to be seen. Let me close with a few key points, and we'll have a little, if we're doing well on schedule, we'll have a little time for discussion and questions. This has to do with environmental cancers. I should point out, I'm going to close with another example, a non-cancer example, but the cancers that are associated with environmental exposures are generally similar or identical to cancers caused by other exposures. The workplace is the high dose setting, and I've spent most of my career studying occupational risk environments, and it's important. Cohort studies of occupational cohorts, and I'm confessing I have a sort of personal bias toward favoring the workplace as a study. They give you the most specific exposure data, but also, with some examples, most examples, you have very small case numbers because you need a very large population to study. I don't have time to show you the data from a study that we conducted in Shanghai, a cohort of 250,000 people, textile workers. But most cohort studies aren't enormously large. And the population-based case control studies have real advantages of you can get large case groups, you can recruit cases and controls, and you can get a lot of information because you're interviewing typically the study subjects or their surrogates. And but the downside to the population-based studies is that the exposure assessment often is based on self-reports, or it's based on crude classifications rather than the advantage of you can put monitors on people, or the industry historically has collected environmental samples that you can use for quantitative dose response analysis and risk assessment. Okay, last example, and has to do with manganese and its relation to Parkinsonism. It's the main form of Parkinson disease. The history of manganese poisoning goes back to the 19th century, where there were French manganese crushers. There were 5 cases. People developed Parkinsonism. It was called gait walk, and tremor, and slow movement. This is classic gait was called cock walk, and people thought this was, at the time, clinicians thought it was, they didn't link it to the manganese exposure. There was a review of some evidence in the early 20th century. The clinical and pathological evidence suggested that there may be some relation to what's now known as Parkinson disease. Study of Moroccan manganese miners in the 1950s showed neurological effects caused by manganese exposure, and Egyptian dry and wet rock drillers in the mid-1960s showed similar effects. And anyway, if you're curious about these actual citations, please feel free to get in touch. I'll send Sandrine a list of references for these. There have been a number of studies of exposures to manganese and other metals. This was a study of Parkinson disease. We've moved away from the cancers, and we'll talk about Parkinson disease and Parkinsonism. This shows the effects of lead and copper relative risk over 5. This is long-term exposures. Lead and iron relative risk of 2.8, and iron and copper relative risk of 3.69. You're probably wondering where's manganese, but that's not typically measured in most workplace environments. This was the auto industry. Welders is an occupation that has long-term exposures, relatively high-level exposures to manganese from welding fume. There have been a number of studies of welders. These are findings for Parkinson disease, and this shows the relative risks in the highest exposed categories. There was a cohort study in Alabama showed in Boilermakers relative risk of 10.3 compared to the general population. This is incidence, not mortality. Other studies, the findings are really quite mixed. And you might say, well, perhaps this was a fluke finding. If you're going to do a risk assessment for what's the appropriate environmental and occupational standard for manganese, perhaps you shouldn't use this. You should use a mixture of all these other epidemiologic studies. Well, this shows the prevalence in the Alabama welders and Boilermakers. And you see that the Boilermakers had relative risk of 10.3. This is Parkinsonism. Welders, 7.3. The welder helpers, 9. And altogether, over 7.5. Very strong dose-response relations. And just going back, this was findings from this particular study in Alabama. Now, we've been conducting a study, and I've been working with my colleague, Dr. Brad Reset at Washington University in St. Louis. And Brad assembled a cohort of about 1,500 welders, and I've since sort of taken the lead on the project. And we've been studying prevalence of Parkinsonism. It's the signs and symptoms of Parkinsonism are, rest tremor, slow movement, and postural instability. And neurologists can identify Parkinsonism cases very clearly with an exam. It's called the Unified Parkinson Disease Rating Scale, motor section UPDRS. And if your score is, the scale ranges from 0 to 108. If you have a score more than 15, that's considered Parkinsonism clinically. And what we've been doing for the past 5 years, and the study is still ongoing, is we've been following the cohort for progression of Parkinsonism signs and symptoms. In fact, the initial result, just the prevalence of Parkinsonism, was almost 16% in the welders compared to other workers, not in the same facilities, but in different occupations in the same region. By the way, I should mention these are welders in shipyards in Wisconsin. And here are the results. This is, it's not a quantitative estimate. We currently have done more environmental sampling in the shipyards, and the industry has provided us with access to their own sampling. And this shows the welding years, and this is score greater than 15. These are cases, and this is normal. And there's very, very weak, essentially no dose-response relation for prevalence of Parkinsonism. What we've been doing most recently for the past 5 years, and it's still ongoing, and apologies for the kind of small print, is we've been looking at progression. There's a baseline survey done of Parkinsonism signs and symptoms, and then we follow them 5, now we're up to 10-year follow-up of the welders. And this shows less than 5 years follow-up, or increase in score of 4.5. These are small changes over time. This was the first set of findings that Dr. Reset published 2017, and basically it shows a suggestive trend of increase in Parkinsonism signs and symptoms over time. And we're about to start year 3 of our extended follow-up to see if we're going to find excessive progression of disease. And the point of this is it's not so much the findings specifically, but findings that evaluate not just a cross-section or just a simple one-time measurement, but look at changes over time are very valuable for etiologic assessment. And with that, I'll open it up if there are any questions and comments, and I hope you find this useful. And like I say, if If you want to get in touch, please contact Sandrine and she'll put you in touch with me.
Yeah, thank you, Harvey. Yeah, I would be happy to do that. It sounds like some of you have been experiencing some issues with the sound. So once again, the webinar will be available in a few days on the HESI website. So, feel free to check that. I will put the address for the site here in a minute. But for now, we're going to open it up for questions. So feel free to type your question in the question box.
Sure. Okay. There's one question there now. I'll go ahead and read it and actually add part of that, something else to the back of the question, but from me. And the question is, are there recent efforts to include biomonitoring sampling more in the EPI study design to produce more reliable data for more quantitative human health risk assessment of substances? And I guess my add-on is any thoughts regarding kind of number of samples necessary, like number of urine samples that you might typically look for urine sampling or other biomonitoring sampling?
Yeah, I'm assuming that this wouldn't relate so much to biomonitoring well, this is my own question. Is this for cancer risks or for other disease risks?
It says for epidemiological study design, and I guess either one, basically. That it hasn't been specified.
Yeah, okay, I can give you sort of a general answer to that. Is how much and what source of biomonitoring you should pursue depends on the nature of the chemical. If you have, a very, biopersistent chemical like the polychlorinated biphenyls, then that's different. You need fewer samples than if you have something that's metabolized very quickly. Lead monitoring, for instance, lead is excreted, but you can do bone assays, and you can get estimates. So there's no simple answer to that. I think the more monitoring that you do, the better. In terms of biomonitoring, sometimes, and I didn't show any data on this for our welder study, but it is helpful to get biological samples of biomarkers of the outcome. For instance, we're studying proteins that are related to Parkinsonism and cognitive decline in the welders that we're studying as other outcomes in addition to just the clinical markers, and that can be a very valuable approach. There hasn't, like I say, I'm not the expert in risk assessment, but I don't believe that the biomarkers, protein markers, are considered a sufficient outcome for risk assessment. But hopefully they'll have more value in the future.
Okay, thank you. I don't see another question yet, but I'll just kind of do a follow-on. Oftentimes, sometimes you see, for example, one urine sample, or maybe at most two in an EPI study. If the substances they're looking at, if you're only occasionally exposed to it, for example, or some kind of ephemeral concentrations or so, any thoughts back about ways to determine whether one is sufficient or not, one or two, or any cautions about taking such few samples for things that may not be particularly good estimates of longer term exposures?
Yeah, I mean, there again, I mean, it depends on the nature of the chemical. If you take something that's, is biopersistent, isn't excreted within, 24 hours, you can get by with fewer samples. Bone lead's the classic example. You can do bone lead measurements radiologically, but with rapidly metabolized exposures, you need to take a lot of samples repeatedly, and ideally, you want to have situations where the environmental exposure has been changing over time, and you have biological samples that the timing corresponds to the environmental exposures. Mm-hmm. It's not easy to do logistically.
Yep. Okay. Let's see, I just don't see any more questions.
There is a question, David, about the age study. So someone asking, I would like to hear more about why Dr. Chekaway feels the AHS has some limitations, even though there is not a dose response.
Well, you're talking about the glyphosate study. Yeah, it's hard to. By the way, the AHS study itself, I think, is an outstanding epidemiologic study, and hopefully it'll sustain its funding from the government in the future. But you know, glyphosate's a difficult exposure to measure, and it varies. It's, you know, I've done a lot of research on agricultural settings. In fact, we're doing some work here in Southern California in studying pesticide exposures in, you know, county just east of San Diego here. It's called Imperial County, and exposures change a lot over time, and it can be a challenge to get clear measurements that are interpretable. So I hope that kind of addresses your question. But the AHS study is excellent, and you know, there's a lot to be learned from that.
Okay, thank you. I see another question. I guess we're getting close to two, but I'll go ahead and read it. How can epi studies be designed better so that instead of mixture exposures in occupational settings, more single chemical exposure is assessed and the effects can be attributed to it?
That's a very good question, and we can't. Let's face it. You know, let's take air pollution for instance. You know, particulate matter. What is it? It depends on where it is. It's, you know, could be hundreds, perhaps even thousands of different components to air pollution, and it's, you know, it's hard to identify the specific causal factors. And when you have a mixture of exposures, and in our lives, you know, we have mixed exposures. Just think about, you know, where you live and what you do, even what you eat and drink. So I think it's, you know, I know that the risk assessments, it's preferable, of course, to have just a single exposure that's measured over time, but we're all exposed to multiple different exposures. That's one of the advantages of, you know, toxicological research or in vitro studies, because you can control the exposure situation.
Great. Okay, thank you. I think we probably have time for one more. How does Dr. Chekaway explain that the US EPA, EFSA, PRMA, and many other regulatory agencies who are charged with evaluating the safety of pesticides took IARC's evaluation in consideration, and they looked at the data and concluded that it was not a carcinogen?
And this is for which chemical?
For glyphosate.
Oh, for glyphosate.
Yep.
Well, I'll have to, you know, be honest about this. I think that was not the best decision. I think the EPA should, you know, the evidence isn't very strong. I mean, you saw that the AHS data didn't show much, but we need more research on that exposure, and we need more epidemiologic research. And maybe it's not a carcinogen. The same situation occurred with polychlorinated biphenyls. There was a lot of controversy about that. But I think we need to do, you know, the government and other agencies, the European Union and so forth, should be sponsoring research on glyphosate worldwide and other compounds.
Okay, thank you. I think we're just about at 2 o'clock now. Sandrine, do you want to have any closing words? There are more questions, but there won't be time to get to them.
Yes, and Harvey, if that's okay with you, I'd like to relay you the questions later. Would that be okay with you, so that people can get answers?
Oh, sure, absolutely.
Okay, and I know you have to go, so I think we'll have to end now. But I wanted to thank you, Harvey, for agreeing to this, and to all of you, our audience, for joining today. Once again, feel free to email me if you have any more questions. Or if you have any questions about this project. We will be posting something about the next webinar, which will be next month on our website pretty soon. And with that, I think we can adjourn. So thanks again, everyone. And I hope you will follow future webinars.
Okay, well, thank you all for inviting me, and please send Sandrine your questions, and I'll be happy to be in touch. Okay, thanks. Take care, everybody.
Thanks,
Okay.
Harvey. That's all.
Thank you.
Bye.
Bye now.